Well, hello, my Theosophical Lodge buddies. This is Jeff Curtis coming to you again from the Sierra foothills in one more of our little Sunday evening science chats. And I hope all of you are doing well and enjoying the summer as much as I am thus far. Um, So what we're going to talk about tonight is going to integrate some of the topics we've talked about over the last few uh, times together, wherein we spent quite a while developing some of the ideas of relativity. Before that, I had developed some of the ideas of quantum mechanics for you in a few different contexts, and actually over a broad span of years. And what I wanted to get to tonight has to do with quite a deep and wonderful topic that threads through all of it. And it has to do with the nature of this thing we call light. And it's a very laden term. It means quite different things to different people, has a broad range of meanings, actions, uh, applications. So I'm going to be sticking with very much of a almost exclusively scientific and technical kind of discussion. But it does go beyond that. It's bigger than that. And it certainly enters into the realm of human feeling, experience, cognition, emotion, all of it. And so I'll touch on certain little aspects. And then over the course of the next meeting or two, I'll try to do some more of that. This will just be a starter on the topic because it's a long, deep topic, I can tell you. Um, how does this all start off? I'm going to give you. Oh, oh no, I seem to be having some power issues. Just a second, I got to check and make sure my cable is plugged. Okay, I hope that does it. I just saw my screen blanking out and seeming to be having some problems. Uh, I'm going to assume we're good, but if I'm not, I'll be getting a phone call to tell me, hey, what's going on? Um, my own history with this, when I stop to think about it, it's quite a story, and it goes deep. Um, I can trace this back to maybe a certain point in time when I first had my chance to, as a young kid, look through a telescope. I had always been interested in astronomy for whatever reason, just as a kid. It just sort of came out of nowhere. Then, somewhere around the time that I was 10 or 11 years old, I had this great good fortune. Uh, Blessing bestowed, I think, by my mother, taking me to a junior high school someplace, and I got to look through a telescope for the first time. And I can remember two of the things that I looked at. One of them was the Pleiades star cluster, and that was viewed through binoculars. And the other one was a little cheapy telescope that was set up and gave me my first look at the planet Saturn. And oh my goodness. I mean, that was, lots of people will say this. Lots of people never forget the first time they see Saturn through a telescope because it's just so grand and just glorious in the way it just hangs there and shines. And it looks like the pictures they've seen in the books, or at least it looks enough like that that they know what they're looking at, and it's amazing. Okay, so I was one of those people. And it sort of stopped the world and gave me an immediate sense of expansion, and I felt like I had touched something important, something large, and made a deep impression. You know, it still gives me chills to talk about it. Um, so that was a biggie. Now, I've never forgotten that since, and as I've gone on to learn more and more about light and use it in my personal applications as a chemist in the lab, uh, the topic of light has always been a little larger than life for me. It's always, I've always known it connected to something big. And so in that vein and along those lines, I'm going to do a little aside here and mention the fact that if you look into the ancient Greek concepts of light, you run into some very interesting things. I spent a little while this morning digging through that. And what's fascinating about it is that you see a sort of a prehistory around 400 to 500 BC, where different schools of Greek thought are having arguments about light and what it is, and also vision. Their discussions about light were very tangled up with vision. And they were having the very same kinds of arguments that came back around again in 1600s, 1700s, 1800s. But let me just summarize a little bit of what was being said by whom. So some of the first opinions and ideas about light were put out by the Pythagorean school and his student Empedocles in around 500 BC. So that's pretty far back there. And Pythagoras, I think because he was very mathematically sophisticated and he was also very into sound, right? He knew about vibrations. And he had a concept of the relationship between vibrations, like of musical strings, and waves. And he, incredibly insightful guy, given the primitive nature of the apparatus that he had to work with back then. Pythagoras and Empedocles, they thought light had a wave-like nature, or it had something to do with a wave-like phenomenon, which is just fascinating to me. Now, they went on to, the Greeks had sort of different ways to look at this. So, for example, Euclid and Plato and Socrates, they thought, that this is a little bit later in time, that the eye sent out filaments of something that touched objects in a way that would somehow relay information back that could be perceived and processed and appreciated and used. Some vagueness on the details of how the information came back, but there was something moving out, was their main sense of what was going on. There were other groups of them who, I think Lysippus and Democritus, they thought it had more to do with tiny particles of something. This was around 430 BC, that were coming from a luminous object into the eye. So we've got filaments going out, we've got particles coming in, we've got waves doing something. And, you know, I'm sure they had grand arguments about it all together back there in the day. And I didn't get around to writing down what Lucretius had to say, but I'm sure he would have had something to say. He had something to say about everything, and it was usually pretty worth it. So that's interesting to me. I like it just because it involves this notion of touching something. There was another cute little nugget that came with Empedocles, where he kind of saw both of these points of view, objects going in, objects going out, and he kind of had an idea that something important happened when the emanations from the object and the eye met, and that there was some kind of a dual functionality of both out and ingoing emanations. That is incredibly prescient, and don't let me forget about it. I'll loop back to it again, either in the very end of this talk or in the next one. So anyway, I personally went on to get involved in chemistry and physics. I was enough of a nerd that, like, when I was in the summer of my 11th year, I think it was, I took a summer off to, maybe when I was 12, to grind a telescope mirror, which was this incredibly fastidious, interesting thing to do. And it taught me a lot about optics. So I ended up teaching myself a strong grounding in the laws of optics, and that served me well later. It made my physics classes in college easier, for example. Then when I got into my chemistry training, chemistry sort of grabs what it needs from physics in order to use it in the lab and in the construction of ideations of molecules and the context of quantum mechanics that chemists tend to care about, which is sort of a subset of quantum mechanics as practiced by physicists. Much of that has to do with construction of instrumentation to use in investigating chemical phenomena. And I started learning about that kind of stuff. One of the things you start getting introduced to long around sophomore year of a chemist training is the science of spectroscopy. And you may have heard of that word. Spectroscopy can mean a broad range of things, but in the most general sense, it's a way of measuring and recording the interactions of light with matter. Now, the physics of that is vast, because that which we call light starts off in our minds and in our definitions as visible light. But that's just a little tiny slice of the electromagnetic spectrum, which is just this huge thing that runs all the way from gamma rays on one end to microwaves on the other end, radio waves actually, on the low end. So many, many orders of magnitude of frequency and energy scales involved there. There's a relatively few subsets of those frequencies that get utilized for spectroscopic information garnering in a chemical context in a chem lab. And you start learning about them when you're a sophomore in chemistry. And I did that. I went on to learn how to use different kinds of spectrometers, particularly UV visible and infrared spectrometers, but also nuclear magnetic resonance spectrometers and microwave spectrometers, and 4 or 5 different kinds that I got exposed to in my first 4-year training. What they're all about at a certain level is using light to drive transitions between quantum levels of either atoms or molecules. And I've talked enough now about quantum mechanics and atoms and molecules to you folks. I hope that some of you kind of remember that, or at least have heard about quantum mechanics, and you know the idea of quantum states. So if a quantum scale object can exist in a ground state, usually there's an excited state that can be accessed by absorption of radiation. So that idea can be sort of depicted in this graphic here, where we start in some ground state. What I'm illustrating for you here would be a ground state with an electron sitting at some allowable energy level. The vertical scale axis here is energy. I forgot to label that, but energy is on the vertical axis. HF, that stands for a photon. That means Planck's constant, h, times the frequency of oscillation of a photon. I'll come back to that in a minute. And if there's a mechanism for that photon to couple its energy into the system, then you can get what's called a quantum leap or a quantum transition, wherein this electron in the ground state is popped up into an available excited state. And now you see the electron, that little single-sided arrow, is residing at a higher energy. And we call that a molecular or an atomic excited state. And there are different kinds of excited states. Sometimes the quantum excited state is a vibrational state of a molecule. Sometimes it can have to do with the orientation of a nuclear magnetic spin in a big, strong magnetic field. That's called, in chemistry, we call that NMR. In hospitals, they call that MRI. There's a bunch of different contexts for this idea of light promoting transitions between allowed quantum levels. that are defined by actually solving the Schrodinger equation and going deep into the nature of what reality is doing there. Now, what's a photon? Okay, so we're getting back to the topic of light and what is it? All right, I'm going to show you sort of a crude cartoon model of how we teach students what a photon is at the sophomore level in chemistry classes. Because this conveys enough information to explain and do a lot. So you look at this little funny thing I've drawn here. What I'm depicting there is a direction of travel. That's the arrow going down and to the right. And the up and down envelopes of oscillation represent mutually perpendicular oscillating electrical and magnetic fields. That's why we speak of electromagnetic radiation. And the basics of this little cartoon come out of the work of James Clerk Maxwell, who extended the work of Michael Faraday having to do with electric and magnetic fields. And the way I've drawn this, I've got space along that straight line, that ray, that represents travel through space. And lambda is a wavelength. So in order for this little piece of light to go through one complete oscillation, it does it over a certain distance of travel in space, and that would be the wavelength lambda. Now, if we want to just to get a little bit numerical about this for a minute, lambda runs from about 380 nanometers to 660 nanometers. That means it spans from the sort of deep violet indigo on the short wavelength in up to 660, the deep red. And a nanometer is a unit of length. It's 10 to the minus ninth meters, so it's pretty small. Meter, you know how long that is? It's about a yard, right? Centimeter is 100th of that. Millimeter is 1,000th of that. 1,000th of a. Now you've seen a millimeter. It's a little fine decrement on a ruler, about a little smaller than a 1/16 of an inch. 1,000th of a millimeter is a micron, and that gets you down to the size of bacteria. 1,000th of a micron gets you down to nanometers. Well, photons, that wavelength of a photon is in the range of hundreds to thousands of nanometers. That boosts it up to tenths of a micron. So photons, how long is a photon? Well, a visible photon is smaller than most bacteria. Bacterias are about 1 micron. That would be 1,000 nanometers. But, they're not unimaginably small wavelengths. But that's just a wavelength of oscillation of an electromagnetic disturbance. It doesn't really say what the photon is. I'm not saying a photon looks like that. I'm saying that we can use this model to explain certain aspects of how photons behave, how their waves diffract, refract, interfere. We get a predictive handle using this picture. And that rate of oscillation, F, is the frequency. And the energy of light turns out to be equal to a thing called Planck's constant, which is a very tiny, small little number, h, 6.63 times 10 to the minus 34th joule seconds. And we can rewrite that. So the energy of light is also equal to Planck's constant times the speed of light divided by the wavelength of the light. So there's lambda up there in the top of the view and now also in that little equation. So the shorter the wavelength of light, the more energy it pumps. And that's because the higher the frequency is. So, boy, we get all over that. We apply that. We learn all different contexts and how to use it to probe the nature of molecular reality in the course of a chemist's training. You sort of end up getting spectrophotometric eyes, if you just look at a light, you know about how many nanometers that light is. If it's red, you know it's down around 650. If it's green, you know it's around 400 and something. If it's deep, beautiful purple, oh, that's getting to be about 400 and between 410 and 390 nanometers. So that is kind of a weird intuition that one develops along the way as part of being steeped in light as a chemist. Okay, so that lays some basics, and it doesn't tell you what light is. It tells you some things about light. So on to the next historical period I wanted to cover. This has to do with the time of Isaac Newton and moving onward, because the debate about light never got settled by the Greeks, and I don't know exactly where it went from there, but I doubt it progressed a whole heck of a lot until Isaac Newton came along, because he was sort of the next huge figure in intellectually pushing physics and mathematics and going to the next level of a quantitative understanding of the universe. Isaac Newton, around 1670, really turned his mind to the topic of light. He was working with prisms. He learned a great deal. It's very interesting to look at the writings of Isaac Newton and the sophistication of experiments he thought to do. He discovered infrared light, for example. He found out that, visible wavelengths of light, it's well known that if you make them intense enough, you can feel heat being delivered. But there was also something beyond the red end of the spectrum, an invisible wavelength that nonetheless delivered heat, and that's infrared light, and yet that was discovered back around this time in history. They didn't know still what was right. Is light a wave or particles is coming out of the... I think they had dispensed with the notion that it was coming out of your eyes. They weren't going on that basis anymore, but there was still a very lively debate. Well, Newton, based on his experiments, even though he knew light exhibited some wave-like properties, he nonetheless held the theory that light consisted of little particles. It was corpuscles. It was some kind of ephemeral, we don't know what, little pieces of something that get emitted under certain circumstances. And those circumstances seem to be electrical discharges or flames or sufficiently hot objects or a few other odd circumstances. They didn't really know the full range of every place light could come from at that point, but they knew some of them. Well, Newton's experiments were never convincing to anybody but himself, quite. And so around 1678 came the work of a guy named Robert Hooke, that's Hooke, and a Dutch optician named Christian Huygens. We have a satellite up in orbit someplace right now is named after Huygens. They had run a bunch more experiments and reinterpreted Isaac Newton's data. So, and they were in a big confrontation and arguing. Well, Hooke and Huygens and a few other prestigious workers of the day kind of won the day, and they amassed enough proof to show that light would reliably and reproducibly exhibit wave-like properties. Those have to do with things like refraction and diffraction, also interference effects. I don't have figures here to quite define those for you, but let's suffice it to say that these are optical experiments that show that you can get light waves to cancel each other and produce both brighter and darker patches depending on how they overlap, and a number of other experimental manifestations that you really cannot explain with anything other than wave mathematics. And so that thinking won the day. I think Newton was quite dejected by this. He was kind of, by all accounts, sort of a sensitive guy, didn't like losing arguments at all. But he did sort of lose out on this. And light came to be accepted as a wave-like phenomenon. But a really interesting question surrounds, all right, it does stuff that we can only explain with wave-type mathematics, but waves of what? What's waving? Waves of what in what? And so from that question developed the idea of something called the luminiferous ether. And this luminiferous ether was a invisible, tasteless, massless something that was thought to pervade all of space, and time, I guess, although they weren't really linking the two ideas up so much back then. And it was just presumed to be there. It had to be there, right? Because light can go everywhere. Light can go through a vacuum. They validated that. So the ether is the thing that has to be vibrating or waving, and it must be there in a vacuum. And so, yeah, there's ether. Let's see if we can figure out what it is, find it, work with it. They never could. No experiment ever was able to say anything, ever say boo about what the ether was. Finally, a very sophisticated experiment based on advanced optical methods called an interferometer was brought to bear on this question by two scientists named Michelson and Morley. This happened in about 1887, so we're almost in modern history now, very late 1800s. And they ran this experiment. I'm not going to draw out this interferometer. Suffice it to say, it's a very sensitive way of comparing paths of distance traveled between two different light beams. And what they did, very interesting, they knew enough about orbital mechanics to realize that the Earth is going really fast around the sun. Well, that means the Earth is going through this ether stuff, whatever it is. That being the case, it stands to reason that the speed of light in the same direction as the Earth is moving through this ether and hitting it as a bow shock should be different than the speed of light the other way, where we're receding. And they tried that experiment over and over and over at higher and higher levels of precision, and friends of theirs tried the experiment. They were never able to uncover any kind of what we would now call anisotropy in the speed of light. They were able to measure the speed of light quite accurately, and it stayed the same, whether they measured it in the same direction as the travel of Earth or in the other direction. And I can't reproduce all the arguments here in a brief presentation, but this was convincing. The scientists of the day thought about it, looked at it, pondered it, and realized, we have a problem. Light, yeah, it has wave-like phenomenology, and yet there's no ether. There's nothing that's waving. What are we going to do? So the field was in a state of crisis, let's say, around the late 1800s. And spectroscopy was being invented about that same time, which is really interesting. First, in the context of atomic spectroscopy. All right. So, next big tick of the intellectual clock comes with Albert Einstein. What Einstein did, in fact, the reason he got his Nobel Prize, essentially for inventing quantum mechanics, was he sat down and he collected a whole bunch of data that had been gathered by different laboratories and workers who were studying something called the photoelectric effect. And you may have heard about this, especially if you've watched very many lectures on the development of science. The photoelectric effect had been seen by many workers and characterized to a sufficient degree. There was broad agreement on how it behaved, not perfect agreement, but Albert Einstein, as a theoretician and a brilliant mathematician, he ended up getting the Nobel Prize and creating an entire field, not by being a brilliant theoretician. This is so interesting to me. This was not his mathematical prowess. This is not the part of Einstein's brain that invented relativity. He just sat down and looked at all this data about the photoelectric effect and interpreted it with deep physical insight. And so I'm going to describe that to you now, what that is. So a photoelectric effect is something that happens if you take a piece of metal, that's that square figure there in the middle, and the weird-looking stuff that you see dribbling off to the right there means that we're taking a battery and charging that piece of metal up negatively relative to ground. That means we're making that piece of metal slightly electron-rich relative to earth ground. And then you shine a controllable light beam on it. This is all taking place in a vacuum, by the way. So coming in from the left there, you see I've drawn it to look like a flashlight. That's a light beam that is adjustable in two key ways. We can adjust the intensity of the beam, meaning how much light per second, what's the light flux coming out of that, and we can also adjust the color or the frequency of the light. So we can shine purple light out of there, which you'll recall from what I talked about a minute ago would be relatively high energy photons. Or we could shine low energy, say yellow or orange or red photons through that beam. Well, when we shine the light beam onto this piece of metal that we have charged up negatively relative to ground, what we discover is that electrons are ejected. And that's what I've tried to draw there as being coughed up out of the surface and flying off into space. That's an electron going into an electron detector. And that electron detector has methodology in it which can analyze how fast the electron is going. In other words, it's kinetic energy. Is it just barely dribbling up off the surface of the metal, or is it zinging up off the surface of the metal? So this experiment relied upon quite some finesse experimentally. They had to be able to adjust the light intensity and frequency of the incoming beam. They had to put this all in a vacuum. They had to be able to charge it up relative to ground and make it negative. And that electron detector was probably the hardest part of it all, which is to not only detect electrons hitting, but also then measure the rate of travel of them coming up. Okay, so upon really looking over all the data and deciding where's the strongest data, where are the really bulletproof observations that we can believe, there's two main observations, and I've listed them there as bullet points 1 and 2 below. The first one is as you turn the beam energy up, the color, going from red to orange to green to blue to purple, what you find is that the electrons come off of that metal surface with more and more speed. The light's coming in. The more energetic the light, the faster the electrons are being blown out. That's okay. That's telling us something. And in fact, when you got to the wavelengths of light that were long enough, far enough into the red, the electrons stopped coming off at all. There was a threshold energy. That's another subtlety to the observations. Okay, observation number 2, the next one I've placed there, is that if you turn up the beam brightness, which means flux, the amount of light per second hitting the target, the electrons would all keep coming out with the same energy, but their number would increase or decrease in direct proportion to the brightness of the light. So there was something statistical being said there. There was some kind of a one-to-one correspondence between something that has to do with brightness of light and the number of electrons being ejected. So that data had been sitting around at various levels of refinement for years. Einstein came along and had sufficient insight, physical insight, into experimental data to be the guy to put it all together and say what it meant. What it meant was that light, despite the fact that it has wave-like properties, is coming in little pieces. And Newton was right. Newton used the word corpuscles. Einstein used the word quanta of light coming from that beam. I forgot what the word the Greeks used. I should have written that down. I'm sure they had one. But okay, so there were a couple of the ancient Greek schools who thought light came in little pieces, little Here it is again, smack bang right at us. The wave-like properties had been proven. They were reproducible. They were there. But there's no ether. And light's coming in little pieces. And so what Einstein came upon there was a thing that we now call the wave-particle duality. And that it was a huge revelation and revolution in scientific thinking, was to realize that light, whatever it is, it has these two dual aspects that are both absolutely necessary. It's not an either-or. Anybody who wants to turn it into an either-or argument has now officially missed the plot. It's both. It's both and. Depending on what kind of experiment you do, you're going to see more of the wave-like property or more of the particle-like property, the quantum aspect. Later in time, I forgot the name of who it was, coined the term photon. So these quanta of light were renamed photons, and that's where we get photon torpedoes, for example. Photon is a word that's all over the place now, and most people kind of know what it means. It's the absolute smallest possible packet of light energy. Okay. So that is sort of where this came to rest, and it knocked the physics community on its butt. Einstein got a Nobel Prize for it because it had such deep and far-reaching ramifications. And physics community hasn't recovered since. In fact, we just go farther and farther. Now, some other fun facts about these photons. They're massless. They do not have what's called a rest mass. And yet, they carry momentum. They carry linear momentum. If you shine light on something, it actually gives it a little push. And they carry angular momentum, or spin momentum. So that's weird. And that's... The mathematics of that is deep and ornate, and maybe I'll try to develop it a little bit next time. I'm going to have to relearn it myself. It's such a bizarre, contradictory thing. This is where we sort of have to let go of understanding the universe. Up until this point, classical physics, it was pretty okay to expect to be able to understand what was going on, but here we just have to let go and realize we can't understand what's going on. We just sort of have to accept it and deal with the fact that our experiments can tell us very confusing things that do not make sense to our human-born egos and perceptual apparatuses, and we just have to get over that and learn to be comfortable with it and retrain our intuition into a different realm. Now, I was going to go take this discussion back a little bit into how we are going to hook up again with relativity and take this discussion to the next level, because I'm not going to do that. I think I'll leave it till next time because I think I've given you enough to think about. But where we're going to cycle back to is that idea that kind of enlivens some of my own interest in this and keeps me going with it. And I hope some of you connect also. That notion that when you see something, when you see Saturn in the telescope, and you feel like you've touched something, and the world has briefly stopped, and suddenly you're bigger than you used to be, that comports with the way some of the Greeks used to talk about it. And it also comports with some of the quantum mechanical theories that are out there now. Particularly, I find one of the interpretations of quantum mechanics called the transactional interpretation of QM. And so I'm going to leave it there, and we'll get back to this next time and try to take it in to the next level. And it's been nice to be with all of you folks. I hope you have a great week. And I'll see you in 3 months or so. And be well. Good night.